what is new for liquid argon dune module 2 will be that one would move from the wire electrodes to the concept of printed circuit, multi-layer printed circuit board anodes. The concept was generated by Francesco Pietro Paolo from CERN and Bo Yu from Brookhaven. Bo Yu, by the way, has designed all the wire electrodes for microdune, protodune, coming for module 1 in Dune. So this will be covered in some other talks here. This particular set of electrodes will also have a shielding plane here, in addition to the three views of the readout planes. Moving on, want to show you what is essential to make any TPC work. It is how one, and to reduce the sources of excess noise, is to treat the electrodes, the readout electronics, integrate the electronics with the electrode, and consider the whole design as an integral concept contained in the Faraday cage comprised by the field, by the cryostat, by the feed-throughs and readout of the second stages of electronics on the out. And the last slide on the charge readout I'd like to show you is the role of cold electronics in the charge readouts. The plot shows the noise as a function of active wire length on one axis and of unnecessary cables if the electronics is outside. So the noise increase is for the warm electronics, this is for the cold electronics. The numbers achieved in practice were, as I have shown, microdune 400 electrons, protodune at about 660 electrons, having longer active wires. Icarus, which is in the short baseline detectors one, which was pioneered the developments of the liquid argon TPCs, however, using warm electronics, has higher noise in here. What this shows is what Dune would look like in noise if it had external electronics, so it would hardly make possible the 10 kiloton large modules. From this I move to the light sensing. The light sensing has some unique problems. There is a vast literature on CPMs, and that all of that vast literature is concentrated on small CPMs for positron emission tomography, medical imaging. The quickest way to get familiar with this to select 3 papers from the special issue of NIM that are listed here. However, there is in all that vast literature, there is little about the readout of very large photodetectors. So that's our problem. We start looking at CPMs, the difference that you design the CPM for PET is the addition to the quenching resistor, there is a little capacitor in parallel, which then causes a spike, which is useful for very fast timing in PET. This is not likely possible for larger pixels and very large area CPMs, where then that capacitor would be negligible compared to the total detector capacity. A critical parameter is the quenching time constant, the product of this resistor and cell capacitance and quenching resistance that I will mention later. The challenge we're facing is shown by in the NEXO readout, where NEXO is the cylinder which has been shown covering 4.6 square meters of CPMs. This is a large area, would be read out in something like 7,000 to 8,000 electronic channels formed in tiles and subarrays of several centimeters. The readout challenge is that the total capacitance of this subarray is of the order of 5 to 12 nanofarad in the best case. The total is about up to 50 nanofarad, depending on the type of CPM. So in NEXO, detection of NEXO double beta decay depends critically on detection of single photoelectrons with good signal-to-noise ratio. The next challenge falls in is the readout for June based on Arapuca. The Arapuca is a really nice creative design, I think specifically determined by the group of people in Campinas, Brazil. Readout of Arapucas is a totally different problem in the sense that while Arapucas is extremely effective in reading out large optical area by a very small CPM area covering less than 2% of what the optical area is. However, that total of CPMs has a capacity. There's 160 small CPMs planned in one this Arapuca design, adding to 200 nanofarads for the lower capacitance CPMs. If one opts for lower voltage CPMs, one ends up with even more. That creates a problem. What is the problem? The problem is this tremendous mismatch between the CPM total signal has to be taken to a transistor in ideal case. Even if you take the largest transistor, the fraction of charge that would arrive on transistor is given by the ratio of these capacitance. So what we see is part in 1,000 or 10,000 of the total avalanche charge. This is a long way from the optimal sharing of charge. So since this is a capacitance mismatch, you can think of doing some capacitance matching. There are three ways you may think of: is adding transistors in parallel, using an electromagnetic transformer, or using an electrostatic transformer. The adding transistor in parallel, conclude quickly, is not very effective because it increases the power you gain very slowly. The ferrite transformer, the electromagnetic transformer, works very well, has been used in liquid argon calorimeters. But for Nexo, it's not practical, it's not radio pure. Could be considered in other calorimeters. So what remains is the electrostatic transformer, which essentially is series connection of CPMs. The numbers you would need for full matching, you would need a relatively large number, maybe 14 for these. You would need more like 28 of these series connections. In practice, you'd like to limit that to 2 or 4, which gives then a corresponding improvement in noise. So that would be the solution one would follow. The readout then is you still remain mismatched. And then comes the big conceptual step. We say we leave all that charge that doesn't want to move adiabatically, which means without pushing it by adding energy from outside. And we take only the small fraction that moves adiabatically from the big capacitor to the transistor. So I will leave you, this would require a long separate discussion, but it allows us to read large capacitors with a small decoupling capacitor, transistor being tens of picofarads, CPMs being tens of nanofarads, and coupling being very small, only much larger than a transistor capacitor. Conventional approach doesn't improve the pushing all the charge out, doesn't benefit signal to noise. So we had to demonstrate that, and for a practical circuit for Nexo, and using N equal 2 to read 20 nanofarad subarrays with liquid argon ASIC tested in liquid nitrogen. The detail that the noise is slightly different, but not much in liquid xenon. So the weak coupling here is just the small capacitor with all this large detector. This to show the results, the demonstration of 20 nanofarad subarrays with liquid argon ASIC. That is the ASIC used in microboon, very low power dissipation of a few milliwatts, and shows you with response to 1, 2, 3 so photoelectrons driven by an LED. In this case, this shows the response to a single photoelectron sample at 2 megasamples per second. The signal to noise resolution ratio was about 60 for the nominal avalanche charge that you get at 0.4 picocoulomb at overvoltage, CPM overvoltage of 4 volts. The one photoelectron resolution was around 3.5%. 2 such arrays were tested, and what's of interest in Nexo is the coincidence between 2 subarrays is less than 20 nanoseconds. So looking a little more closely, the sampling was at 2 megasamples per second. The anti-aliasing filter was performed by this liquid argon ASIC, according to Nyquist criterion with 1 microsecond integration time and peaking time. And the timing resolution was given by simply peaking time times the shape constant over signal to noise ratio. So this is how this works. So now looking at what we want to do for the much larger capacitances such as Arapuca, the question we also face is to ask, is the CPM design optimal for large area photodetectors? And one can examine this question and looking at signal to noise, which I shown in previous slide, which is essentially dependent on the transformation ratio N. So for Arapuca, we use assume N4 instead of N2 for Nexo. And if you want to read out single channel, the numbers you will get is due to the much larger capacitance of 200 nanofarad, you would get signal to noise for single electron about 12. And the timing accuracy of 50 nanoseconds. This is okay for time 0. If you want faster response, faster response, signal to noise will suffer, go down, and then one will be forced into more channels. But you can start looking at Arapuca from a single channel point of view. You look at the role of the quenching time. You differ CPMs with different quenching time going up to 1 microsecond, going through anti-aliasing filter, you lose on the amplitude. The amplitude starts dropping down, you lose on the slope. So overall performance suffers. Long quenching time constant and short integration time makes the signal increasingly difficult to detect. So that's one aspect that one normally doesn't consider as very important, looking at a single CPM, but the as one goes to the liquid argon temperature, if the quenching resistance made of polysilicon or materials where this quenching time constant would increase, quenching resistance would increase, one would suffer. The CPMs have been made with metal quenching resistors where the quenching time constant was of the order of 100 nanoseconds as needed to suppress the after pulsing. So that's the detailed story. The conclusions and the summary are here, that with large large arrays of CPMs, you can read them out by a weak coupling between CPM input transistor, and that's better, more effective, lower power dissipation, and has some other advantages. And with a relatively small coupling capacity. The message on CPMs is that CPMs with lower capacitance, even with higher operating voltage, offer better signal-to-noise ratio and timing resolution in large area photodetector. CPMs with the lowest quenching time at low temperature, allowed by the quenching process of 100 nanoseconds, offer the best SNR, especially at shorter integration time. CPMs with higher capacity, why does it all matter? If you have higher capacitance, long quenching time, it results and requires certain signal-to-noise timing resolution that would force us into the larger number, more electronic channels, more subdivision, higher complexity, power, and cabling. So it comes at a significant cost in a large system such as for Doom. So I would ask if there are any questions.
So thank you very much. You've timed your talk perfectly.
By chat, I will watch for that.
Are there any questions from the audience?
I did have a quick question. On slide 18, I don't know if you want to go back to it, but on slide 18, I wanted to ask two quick questions. So is there first the sort of the dotted lines that you have for the feedback loop? Was there any particular significance to that, or is it just for ease of readability? And then the second thing is this sort of weak coupling with this CB capacitor. Are there papers or demonstrated examples using this? I'm guessing there are, but if you could mention one or two, that'd be great.
Okay. I think I got the question. Let's go back to. So you are asking about that. Yes, the basics I'm talking about are without feedback. When you look more closely at this circuit, if you make it a charge amplifier, then that presents another view and looking at this measurement, then the ratio of CB and this capacitor gives you the voltage gain between the voltage on CPM and the output. So it becomes a voltage measuring circuit. So why I dotted this is because conventional approach always uses feedback, which tends to confuse the issue. The feedback in that approach introduces feedback both the signal and the noise. It's true here, but this becomes a conventional circuit. It becomes a circuit which receives small fraction of charge through a relatively small capacitance. So more like with most other capacitive radiation detectors. The virtue of this circuit is also that the performance of electronics and the noise is possible to evaluate independently of the condition of CPMs. So not to get into too many details on if there is a defect in CPMs, it doesn't affect the performance of the electronics which you can test independently in a large detector.
Thank you. We have time for maybe one more quick question. Okay, so I'd like to thank the speaker again. That was a very interesting perspective. So thank you very much, Veliko. The next speaker.
Thank you.
Can you stop sharing your screen, please? Perfect, thank you. The next speaker is Laura Palucci, speaking about the DUNE vertical drift photon detection system. Please, the floor is yours.
Okay, hello everyone.
You are not very well audible. Could you please check your mic?
Is it better?
A little better, yes.
Okay, if we have problems, then we'll try to sort it out. Okay, hello everyone. My name is Laura, and on behalf of the DUNE collaboration, I will present the proposal of the photon detection system for the second DUNE module, also known as the vertical drift. So, as we heard a lot already today, DUNE is a long baseline neutrino detector. The source of neutrinos as well as the near detector will be placed at Fermila, and the far detector will be in South Dakota, about 1,300 kilometers away from the near detector. And for the far detector, there will be 4 modules. First underground, and each of these modules, they will employ the LAR-TPC technology, and they should have about 17 kilotons of liquid argon. So the first module that we can see here will have this configuration. So there will be APAs, anode and cathode planes placed vertically with respect to the ground. So the electric field, therefore, the electron drift horizontally, and it's also known, this module, as the horizontal drift. The second module, which is here, will have quite different configuration of things, as you can see in this picture. So the anode and cathode planes will be placed horizontally with respect to the ground. So electrons drift vertically, and that's why it's also known as the vertical drift module of DUNE. The total length here is about 13 meters. It's about 13.5 meters, and the full length is about 60 meters. And this will be divided into 2 volumes by this. This is interesting, for it will probably allow for an enlargement of the active volume of liquid argon, since the only structure that you have placed in the middle of this liquid argon is non-cathode. As we have heard in the previous talk, the anode planes will be contrary to the horizontal drift, where we'll have APAs, which are layers of active wires at angles to each other to form grid. In the vertical drift, the wires array will be substituted by PCB, the charge readout, using stacked perforated PCBs. This is not transparent to light, so as opposed to what will be done for the first DUNE module, where the photon detectors will be placed behind the anode planes, we cannot do that in the vertical drift. So let me just say how these photon detectors will be arranged, and as we also have just heard, will be based on the Asadi technology, and will be large tiles measuring 60 by 60 centimeters square, with 160 silicon photon multipliers distributed here on the lateral of this large tile-shaped
I'm sorry, you are breaking up, so we are losing your voice. Maybe you can try to hold the mic a little closer to your mouth.
Okay, I will try. I'm sorry for that. Okay,
No problem. It is a lot better. Thank you.
Okay, so how the photon detectors will be placed, since they cannot be behind the anode plane. So the proposal here is to have 3 planes of photon detectors. So photon detectors placed over the 2 longer laterals, as listed here. So 4 photon detectors on top of the volume and 4 photon detectors on the bottom. So close to the 2 anode planes, and these photon detectors should be placed over the cryostat wall, so behind the field cage. And more photon detectors being placed here over the cathode. With these, we'll have 3 sites of active coverage for photon detection in this volume. These, of course, require a modification of the field cage in order to allow photons to pass in a reasonable amount to leave the field cage. And the anode will be partially reflective to light. So over the full area, an average reflection of 15 to 20% is expected, at least for a given range of wavelengths. Since we'll have very large distances here on average between that the photons need to travel to reach a photon detector, xeno doping is also included as a mean of increasing the photon collection in this large detector. And with this, we should have about almost 15% coverage over the cathode and about 7.4 over the 2 longer laterals. This should allow us to have good uniformity of response, low detection and trigger threshold, and also energy and position resolution capabilities. In order to evaluate initially preliminary the capabilities of the system, it was created a simulation, standalone simulation using GN4 that we can see the structure here. So we simulated the top volume, so half the total drift, placing the photon detectors, checkers, disposition that you see here. We also included the field cage structure. As I mentioned, it has to be modified using narrower profiles for this 60% of the total length here. And we used these you can see here in order to simulate light propagation and reaching the photon detectors. Preliminary, we have this light yield map that you can see here. This is for the a central cut of this detector. So if you see here, this is Z. We have Y vertically and X. So we have a cut here in an XY plane, and we can see the light yield of every point inside this plane. And we have here the assumptions that we made. The assumptions are that we have an amount of xeno doping, which is enough to transfer as 175 nanometers light from xeno emission. And then we see that the light yield map, it's fairly uniform, as you can see here. We have an average light yield of almost 44 energy deposited, and a minimum per And those are very interesting numbers. They are above the requirements that we have for the far detector 1. And they are important for the detection of supernova neutrinos and also for nucleon decay tagging. We have also made an exercise by determining the position of very low energy point-like energy depositions in this volume. So from simple barycenter determination, so completely geometrical determination of the point of energy deposition. And here we can see the resolution we can obtain for each of these three axes for energy deposition right in the center of the top volume. And we see this a little bit less precise direction, since we have less photon detectors, less coverage over the laterals. If we try to make the same thing for anywhere in this volume, we can start seeing some border effects. So we have a worse resolution, especially for the X here compared to this one. So these are well within the requirement that we have in order to allow for the matching of the signal from the photon detectors and the TPC.
1 more minute.
Okay. We have also made energy depositions, so energy resolution that we can see here that we can get better than 10% for energy depositions of 3 MeV. And also we have analyzed a preliminary the trigger efficiency that we could get. So using a simple majority condition on close trials. And this is for events happening at the center of the volume and increasing distance to case the cathode. And here for different energies. So of course, the larger the energy deposit, the better you get the efficiency for triggering. And of course, as you losing a little bit this majority condition, you also have more efficiency, but you can also have less purity. That is still one thing that we need to do. So very preliminary, we have identified that the vertical drift PDS has the capabilities of allowing for a very high, low energy threshold for detection. We have a preliminary light yield map position, an energy resolution, and also trigger efficiency. And this is very exciting since this points to an interesting possible improvements in low energy physics, including, for example, supernova, improving supernova neutrinos, solar neutrinos, and perhaps allowing the capabilities of detecting the diffuse supernova neutrino background. So thank you.
Thank you very much. We have time for at least one question. I have one. So how do you achieve the reflectivity of the anode planes? Is this optimized in any way?
Not yet, but there is this possibility that you can use the structure of the PCBs and try to change the material in order for it to be more reflective. And I forgot to mention, and we are only considering reflectivity for the xenon emitted light and not argon light. But we can change materials and we can polish the surfaces in order to make it more reflective. So this is something which is, let's say, on the radar for improvements in this system.
Okay, any other questions? If not, thank you once again. Our next speaker is Ryan Durrell, talking about the wavelength shifting performance of polyethylene naphthalene films in a liquid argon environment. Please go ahead, we can see your slides. Maybe you can start the slideshow.
Okay, how's that?
Well, it's okay. We can still see the rest of the window, but I think the slide is readable.
Okay.
So go ahead.
Okay. Hey, everyone. I'm Ryan from Illinois Institute of Technology. And today I'm going to present some work that we did along with Jonathan Asadi's group at University of Texas at Arlington. So he's the next speaker, so be sure to stick around and see his talk coming up. We put out a paper last year about this that you can see on GINS and on arXiv. You can see our collaborators here. And essentially what this is about is wavelength shifting coatings for noble element TPCs. So normally I give a whole introduction about LAR TPCs and how they work, but I'll get right to the point here today since we already heard so much about that. So essentially liquid argon gives you scintillation light in the ultraviolet, right? But many of our light detectors, they only detect visible light. So there are a lot of potential solutions to this that we can even imagine up, including direct detectors for UV light, which some folks are going to talk about. But one other solution is wavelength shifting coatings. And the industry standard for these coatings is TPB. And the reason why is it has pretty good
I'm sorry to interrupt, but
Sure.
your slides are not progressing. You're still on the title
Oh, really?
slide.
Okay, I'm sorry. Let me see. Does it look better now?
It does, yes. Thank you.
Okay. So I'll go this way. I guess it's the full window. Adobe isn't cooperating. So luckily you didn't miss that much. I was just on this slide here. And to get back to where I was, I'm talking about this stuff called TPB, which is our wavelength shifting coating used in a lot of experiments already. And it's got pretty good efficiency turning ultraviolet light into visible light. The reason we want to consider other potential coatings is that TPB is expensive. It's a little bit difficult to use and requires vacuum coating on surfaces. And in that sense, since you have to do this vacuum coating, it's prohibitive for large surfaces in detectors like Dune. There are easier TPB coatings, which can be painted on, but they tend to yield less light. So one cheaper, more practical alternative that many people are investigating is polyethylene naphthalate, or PEN. And there are a bunch of papers about this, including some recent talks and results. And I included some of those in the back here, where you can read more about it. So advantages to PEN, which is essentially very close to common plastic, are it's easy to use and get a hold of. The reflectors can be prepared with a lamination machine, which is essentially about $500. And you can see an example of that on the right there. We have one here in the lab at IIT. Whereas TPB, as I mentioned, it's coated evaporatively and you need a big machine like those here on the left. PEN, it's faster to prepare. And it's ideal for coating things like windows or large surfaces, maybe behind your wire planes in a TPC. The coatings also tend to be robust. As you know, we make soda bottles out of plastic, although it's a slightly different kind of pen. And finally, yeah, pen can be bought from many different vendors. So we tested supplies from 4 different suppliers. So further motivations, there's a study done in 2019, also by Jonathan Asadi, investigating the stability of TPB over time. And essentially what they did was immerse some light guides into liquid argon over a long period of time, of about 72 hours. And some of these light guides were coated with TPB, others were not. And sometimes they also use foils. And they observed count rates in their light detection system. And with the things that weren't coated in TPB, their rates of counts were essentially stable, like you'd expect. But with the TPB, they saw counts that were rising over time. They followed this up with measurements by molecular sieve, and were able to see that the TPB had emanated into the liquid argon and hadn't been super stable. So another question we had, in addition to how does PEN compare to TPB in terms of performance, was is PEN stable or at least more stable than TPB? So here's our test setup, including our liquid argon dewar there. That's the big metal thing in the middle. And our electronics on the right. It's very hard to see, but they're tiny little MPPCs or SIPMs from Hamamatsu on the green board. Our sample is on this kind of reflective shiny thing on the upper right. And it's attached to an ESR reflector. And then to the left of that are alpha sources, which create our radiation or scintillation light. We then read these out into amplifiers and NIM electronics. So our data taking procedure, relatively simple, but we observed count rates with our electronics off to make sure they're 0. Then we observed dart counts with the electronics on and our source inside the argon. And finally, then we emptied out, put our alpha source in, and observed count rates over a period of 6 to 8 hours. And once we were done with the sample, we repeat with a new one. So we tested 4 different polyethylene samples from various suppliers, although what we found out was that they were all basically a variation on a material called Tionex. And you'll note the first 2 samples were different from 3 and 4, but the 3rd and the 4th, even though we have them as different samples, they were the same type of material, and we didn't initially realize that. We also tested TPB and the bare reflector for comparison. So here's the performance, and the reason I list all those samples is because you'll see there was somewhat widely varying performance between the samples, from very low up to as high as 34% relative to TPB. So pretty good, but this raised some important questions, such as why do all these samples perform so differently? And also, is sample 3 and 4 essentially the same material? Why did they perform so differently? So we had some hypotheses, including the physical and optical properties of the samples. Samples 1 and 2 were essentially clear with some small differences, and then 3 and 4 were essentially hazy. So you could see differences. And we wondered, if this had something to do with the UV wavelength shifting properties. There's also potentially the agent handling and the coupling to our reflector. So we tested some of these optical properties with a UV vis spectrometer. And the results, at least to me, were as expected, where the very clear PEN samples transmitted light better, and the hazy ones had lower light transmission. And then kind of flipping, diffuse reflection off the samples was higher for the hazy samples and much lower for the very clear samples. So that kind of made sense, but it didn't explain all the discrepancies we saw. One thing we realized as we looked at our experimental setup more closely was that sample 3 and 4, although they were the same, one was adhered with adhesive to the ESR backing, whereas one was separated and adhered basically with nuts and bolts. And this allowed liquid argon to flow between the sample and the reflector, giving better reflection. So to make sure this was what was happening the way we expected, we retested sample 3 attached with nuts and bolts, and we saw similar performance to sample 4, so about close to 33% that of TPB. So they performed about the same once we had the same kind of backing. There's some other differences. I don't have a lot of time to go into this, but there are more papers you can read, and you can also even see kind of how hazy this pen is on the bottom right here. So interesting. Finally, the emanation studies. So we wanted to test PEN similar to how TPB had been tested with Jonathan's group before, and see if it seemed to emanate as well and have rising count rates. You can see the setup here on the right, where we had G10 holders for our samples with small apertures in them. And note that this sample holder was not directly facing the SIPMs on the left side here. So we then took the data like we did before, however, over a period of 72 hours, so a longer period of time. than those initial measurements, which were 6 to 8 hours. Here are the results. And what you see is the red crosses that are sharply rising at the top are the TPV samples. So once again, we saw these rising count rates for the TPV, whereas the pen was consistent to within about 1 sigma with no rise, although there is potentially a slight rise here. So one follow-up study that could be good for this would be doing a study like this over even longer period of time, and also following up and repeating this study with pen, but with molecular sieve. So when you have TPB and you filter, the liquid argon at the end, you can actually see that there's this kind of residue like in the filter by shining a UV light on it. And we'd like to do the same with pen. So I'm kind of getting to the end of time here. So the conclusions to take away here are that pen is potentially a viable replacement for TPB. The performance varies. In this study, it performed as well as 34% as well as TPB, although some recent studies by Marcin show it may perform even better than that. There was variability between the samples, so how you prepare them and attach them to your surfaces or other backgrounds is very important. It also seemed to show relative stability, although we would like potentially some more measurements with that in the future. So that's all for now. Here are some citations and further reading. There are a lot of other papers we've read and talks that gave us an idea of how to get started or what to do here, as well as our paper there at the bottom. So do we have any questions?
Thank you, Ryan. That was also perfectly timed. I don't see any raised hands in the audience. Please go ahead if there is anyone.
Hey, Ryan, I had a quick question. So aside from PIN, do you see any other wavelength shifters that are kind of competitive as far as the sort of cheap to effectiveness relative to TPV?
That's a great question. At the moment, these are the two main ones I know. Of course, it could be fun to test other types of plastic, but pen for now is the main one tested. But thanks for asking. I wonder if anybody else knows. Okay, so if that's it, I'll go
I have another question. I'm wondering, so this is a usual problem which is challenging to address with these wavelength shifter measurements. Have you tried to assess the systematic on the angular emission from both wavelength shifters? So comparing TPB with PN can give you some effect just because of the smooth surface of PN, which could lead to some total internal reflection. So yeah, did you address that for your analysis in any way?
Yeah, we didn't address, and essentially not counting the emanation studies, the samples were at basically the same angle for the measurements. But yeah, I was thinking about that too, especially noting the discrepancies between the different pen samples and their clearness and haziness and performance in different types of reflector measurements with the spectrometer. Yeah, you can imagine you might see some of the poorly performing samples maybe perform a little better, and vice versa with the good samples. So yeah, I think that could also be a great follow-up measurement. Thanks for your question.
Okay, thank you very much. It's time for another talk. So this would be, as you announced, Jonathan Asadi speaking about selenium-based UV photodetectors. We can see your slides.
Great.
So go ahead.
Okay, thank you all very much. My name is Jonathan Asadi. I'm very pleased to tell you about some of the research we're doing into these novel detectors for use in liquid noble detectors. So as people are aware of, the archetypal single-phase liquid argon TPC that's used for neutrino oscillation physics uses massive homogeneous detectors that offer a dense target in order to give you an appreciable interaction rate. And as Velko mentioned, the animation shown on the top gives you an idea of why we do this. It provides fine 3D tracking with local DEDX information, and it uses 2 or 3 projective readouts to work back to a fully 3D representation. However, that last little point that people often brush over, to take projective readout and go to a truly 3D readout is a highly non-trivial task, and many approaches, algorithms, and reconstruction packages have been used to try to accomplish this to varying degrees of success. Pixel-based detectors solve this problem by recording the data in a native 3D format. The animation in the bottom shows you a concept of this, that as the charge arrives, you essentially know within the pixel's location exactly where it is. This technology has been demonstrated as a viable solution for LARPix, and with a technology known as LARPix, which is targeted to the Dune near detector. And there are new solutions targeting these massive kiloton scale detectors known as QPICs, which offer both low power and low threshold pixel-based charge readouts. The key here is that the intrinsic 3D nature of that data is an essential component for all noble element TPCs. Now, these conventional single-phase liquid argon TPCs use the fact that their wire planes are semi-transparent to the photons in order to place the photon detectors behind them. Now, pixel detectors have an opaque charge collection surface, making that particular solution impossible. The picture on the upper right is a snapshot of the inside of the microboon TPC. Behind it, you can see these large white discs, which are the TPB-coded wavelength shifting panels in front of photomultiplier tubes. On the bottom, you see a pixel detector, a prototype of the Dune near detector, where the pixel planes are shown in yellow. And then what's being hung off of them is photon detectors, which are essentially waveguides that guide that wavelength shift and guide the light to SIPMs, which are mounted on the pixel plane. But the question remains, what if you could actually use the pixel plane itself and the fact that you have an opaque surface there and turn that into an advantage? In some sense, how do you turn the vice of now that you have opaque to something that you could do? Well, what we imagine, or at least I try to dream of, is what if your whole pixel plane could actually simultaneously collect light? A pixel plane which would be sensitive to UV photons simultaneously with the ionization charge could be an enormous breakthrough. Your effective instrument in an area and a detector like this would be enormous. And so even if a device with low efficiency could give you a huge gain in its potential. And what's really interesting is these low power, low detection threshold pixel readout electronics that are being developed could really be an enabling technology to realize this. You could actually allow you to integrate your charge and light readout into a single sensor, where the sensor that we're thinking about in particular is that of QPICs, which I cite the paper here for. So as a concept, what I'm imagining here is each individual pixel would have its corresponding readout electronics coupled to here shown schematically as the QPICs readout that would collect the ionization charge, but then you would coat that pixel plane with some sort of photoconductor that would do the job of converting the VUV light into charge directly, which could then move through the photoconductor and be collected by the same electronics that you have here. So what the search entails is to look for a good candidate photoconductor, and there's a partnership of universities and labs that are working to design a novel idea like this with various approaches to trying different photoconductors. And a really rough set of good photoconducting candidates would be ones that are directly sensitive to VUV light. This would allow you to convert the scintillation directly into signal without some of these pains, as you just heard in the previous talk, of wavelength shifters. Of course, this has to be compatible with cryogenic environments if it's going to be used in many of the liquid noble detectors. So we're looking at operating temperatures of liquid xenon and liquid argon. Ideally, you'd like this to be sensitive to low photon flux, and even better if it could be sensitive to single photons. And then, of course, any solution you put forward here has to be scalable and cost-effective, because the size of the detectors that we're targeting for this are ton and kiloton scale detectors. And if you don't necessarily satisfy all of these simultaneously, it doesn't necessarily preclude you from being a good candidate for particular applications, but we're looking for something that maybe hits a home run on all of them. So this title of my talk is using amorphous selenium, and you may ask the question, why amorphous selenium? Well, there's a number of reasons. One is it's extensively used in X-ray medical imaging detectors. So that provides an actual really nice starting point for just understanding its properties in general. The devices are typically manufactured using thermal evaporation, which on the scale of things is not so difficult to do and can be relatively cost effective. Selenium is not an expensive element. And both, I would say, relatively old literature and some new calculations we've done with various condensed matter colleagues of ours show that selenium has favorable characteristics in the VUV region, that of a high absorption coefficient and a favorable band gap around 2 eV. The plot on the top is data which was taken back in the late 60s, which show the absorption coefficient as measured in the range of VUV photons for both the crystalline selenium, triagonal selenium, and amorphous selenium, which are very similar to one another. And the plot on the bottom is a reproduction of that data with some first principle calculations that were done using density functional theory, along with collaborators here at UTA. So what we don't know, or maybe better, what we didn't know prior to some of the work that you'll see in this talk, is the answer to, is amorphous selenium sensitive to direct VUV light? The answer is yes, as I'll show you in some upcoming slides. Is amorphous selenium compatible with a cryogenic environment? The answer is mostly yes. Again, some details coming. And is it sensitive to a low photon flux? There, the answer, we don't quite know yet. We haven't gotten all the way there, but we know where we need to go. The key here is to get a sufficiently high field so you can get gain. And this has been demonstrated in X-ray based amorphous selenium detectors, but now we're trying to understand how to adapt it to our particular use case. I'm showing you here a picture of one of the first prototypes, which we produced, put with selenium lovingly put on a board that we call the Snoopy board. So we chose initially to think about the prototyping in a horizontal geometry. This is because it's relatively easy to deposit selenium as an amorphous substrate onto commercially available printed circuit boards to allow us to do simple, fast, and cheap prototyping. The horizontal geometry also allows us to apply an electric field between these electrodes to drift holes and electrons for collection, where really the limiting factor here is the strength of the field that we can achieve. And you can do this one of two ways. You either turn the voltage up or you decrease the distance. Commercial, cheap and fast manufacturers have a limiting of the spacings of the traces that you can get down to about 125 micrometers. New technology that we've been exploring with a company here in the US of these high density PCBs can achieve a much smaller spacing and ultimately are targeting a capability of going all the way down to 5 micrometer spacings. And I'm showing you here sort of a rough schematic on the left of what the various prototypes I'm going to go into that we've tested looks like. And on right is a sort of an animation of how we would imagine this horizontal geometry working with this particular pixel technology. So in the last year, we've managed to go through 3 evolutions of prototypes, starting with these Snoopy boards on the left, moving to a smaller board that we could test for various temperature understandings, known as the cookie board in the middle. And then on the right is an adaptation of the Snoopy board where we've gone down to extremely fine spacings, these 25 micrometer spacings, to target higher and higher fields on the selenium board. So the first test we did once we had some selenium boards evaporated was to put them under VUV light in a vacuum. We used relatively thick samples to begin with, 15 micrometer thick selenium and 20 micrometer thick selenium boards with fields somewhere between 0.8 volts per micrometer up to about 7.8 volts per micrometer. And these showed appreciable signals when exposed to a bright xenon flash lamp and gave us good confidence that at the very least we see response to VUV light and that these are signals that we could then take the next step and see is it viable in a cryogenic environment. So we took those boards and cryocycled one of these boards, then followed that cryocycling with a scanning electron microscope using an energy dispersive analysis of X-rays to characterize what occurred to this board having undergone a cryocycle. First and foremost, the board appeared to have survived a cryocycle. We did this cryocycle rather slowly, lowering the board all the way into liquid argon and then bringing it up over a period of 40 minutes. After retesting the board in the same vacuum apparatus, the signals appeared to be unchanged. We chose a specific spot on the board that had a very identifiable strand there that you could see before cryocycling. The picture on the right is an SEM afterwards. You can see the strand has unfortunately broken off, but the residual is still there. You can also see small deformities that have formed on the board due to the cryocycle. If you then perform this EDAX on them and zoom into those particular substrates, you can see that what's actually been exposed is the tin and lead that makes up the PCB underneath it, the traces underneath it. And if you look at some of the other areas, you can see that around in the surrounding cracks, it remains pure selenium. So all in all, after a single cryocycle, this board actually looked like it was in relatively good and robust shape. And there are various methods that we could do to try to improve the evaporation methods that would also then improve the performance during cryocycling. So then we wanted to know, does selenium continue to give us a signal as we go down towards the temperatures that we care about for liquid noble detectors? So we recently built and commissioned a system that allows us to pass liquid nitrogen through a stainless steel line. We couple a copper block to that liquid nitrogen line and then put the board onto that so that we can gradually cool down and then let warm up these selenium devices without actually having to put them in a bath of whatever your favorite noble element is. And then we can expose that to direct VUV light. And we can also monitor the temperature of whatever's happening on our particular board using resistive thermal devices. So this is the punchline of what we got to see with data taken very recently. It's actually the first time I think amorphous selenium's been tested below 166 Kelvin, at least that I can find in the literature. We didn't quite reach all the way down to 88 Kelvin, the target for liquid argon during our first run. We got down to about 95 K and then it just was not cooling any further. So we're working on improvements to better help the thermal coupling in the system. We used a very thin board on this particular case, 1.2 micrometer thick amorphous selenium board, which is 10 times thinner than the previous ones. And the signal is proportional to the amount of selenium you have. So we need to find an optimization there, but that explains why the pulses are so much smaller. The data taking during the cool down was taken at a slightly lower field than we allowed things to warm up. And you can see a reduction in what is effectively the electron mobility due to this temperature variation. And we're working now to quantify and understand the mobilities down at these temperatures in order to understand what is going to be the ultimate effect when we go down to extremely low photon sources. So the road ahead for amorphous selenium is to demonstrate that single VUV photon response. And we really needed two pieces for this. First is we needed a reliable pulsed VUV source that's capable of delivering single VUV photons. And there's a talk by a postdoc that works in my group, Austin McDonald, on Thursday that will show you a development of a tool that we made that is capable of doing just that. The second is we need to achieve fields in amorphous selenium that are capable of providing gain. The plot on the top right is taken from the citation given there, where you can see the gain factor shown in the y-axis as a function of field. And to get appreciable gain, you really have to get above 80 volts per micrometer. So there's new work on both the horizontal geometries shown here and some novel ideas with vertical structures that we're doing with the group at Oak Ridge to try to understand how we might be able to achieve this for amorphous selenium-based detectors. Following that, we want to test these devices in liquid argon with a known VUV source, and there are test stands at UTA. The one shown here on the right is a TPC recently built that's capable of doing charge and light measurements with comparison to a known light readout like a PMT shown there on the bottom. And similar test stands are being developed at Fermilab, which are underway of being commissioned in order to prepare for this test specifically. So with this, I'll conclude. Pixel-based detectors offer an intrinsic low 3D readout for liquid noble TPCs, but the opaqueness of the pixel plane necessitates an alternative light detection scheme. Now, a pixel plane which is sensitive to both direct scintillation light and ionization charge could be a transformative step, but requires identifying a suitable photoconductor. And amorphous selenium is a promising candidate because it's cheap, scalable, and has a long history of applications in medical devices. More specifically, the new results show that it responds at cryogenic temperatures and has robustness in a cryogenic environment. Now, there's obviously more tests underway to get all the way down to single photon response in a native liquid argon environment. So I hope everybody will wait for us for maybe or before next year, but at latest next year with some of these results. And with that, I thank you for your attention.
Thank you for this interesting talk. Are there any questions? Well, so I have one again. So I'm wondering about the reflectivity of selenium. Is this nearly as high as for silicon at these VUV wavelengths?
So if I don't know if I have data on that, but we did do those calculations on these DFT calculations that were done. And if I remember right, the reflectivity was lower than silicon for amorphous selenium. But I'd have to go back and double check that in the paper. But we did look at that. I believe some measurements were done in the late 60s, again, probably the same source, but I don't remember that data off the top of my head.
Do you see radio purity as a concern for selenium in general?
Certainly, given some applications, that could be a concern, but we haven't approached that yet because we're not at the point where I'm willing to take it to the people that care about radio purity to say, I have a photo sensor that's ready for you.
Sure. Wonderful. Thank you very much.
Yep.
So the next speaker is Jacopo Dalmason. Could you please share your screen?
Okay, can you see my screen? Oh.
Well, we see your browser window, not your talk.
What about now?
Okay, yeah, it
Okay.
looks better. Now, again, if you could try to start the slideshow.
Can you see it?
Yeah, we see a sort of
The outline. Can you see
view.
the outline?
We see the outline.
Okay. What about now?
Maybe you could change the view so that we don't see the speaker's view. I'm not sure how easily that's done. If you stop the slideshow and start it again, maybe it will just work.
See. I'll just. Can you see the slide now in just PowerPoint or something?
Yeah, I'm also happy to show the slides for you if that's any easier.
Yeah. I mean, I can just show it like this if it's okay.
Well,
only one participant can share at a time.
Okay, then why don't you show it again and at least minimize this additional window on the side.
What about like this? Is it?
Well, now we are back to seeing the agenda. So we lost your.
Hold on. Hold on. Let me try 1 second again.
Perfect. Now it worked.
Okay.
So start the slideshow. I think it will work now.
Let me try just very quickly. If I start the slideshow, can you see the correct
perfect.
thing?
Yeah, go ahead.
Okay, perfect. Okay. Sorry about that. So today, well, first of all, thank you very much for the opportunity to present my work. And today I'm gonna talk about the setup that we have here at Stanford that we're currently you're planning to use to characterize a large area of silicon photomultiplier array, and this is of course a prototype for Nexo. Yeah, I'll go very briefly over the Nexo experiment. I'll explain why we're doing what we're doing, describe what we have right now. And then I'll go just a little bit into the detail of what we are currently upgrading and what we're planning to do with the test that we've done so far. And I'll just show a couple of images of the light simulation that we're doing as well. So as Brian already pointed out this morning and described in details, this prototype is part of the Nexo experiment, and the Nexo experiment is the next generation 5-ton liquid xenon TPC enriched at 90% of xenon 136. And of course, it's aiming to fully explore the neutrino Majorana mass, at least in the inverted ordering. You can see on the top right plot without the sensitivity and the discovery potential goal, as Brian described this morning. So Nexo will rely on three important observable in order to reach the physics goal, which are the energy resolution, the topology, and the event location. And in particular, in this talk, I'll focus on the energy resolution. And the energy resolution, as you can see on the bottom right plot, amongst other factors, depends also on the light collection efficiency. And in fact, in this work, I'll describe and the standard prototype is built exactly to study this dependence. So the current setup we have, it's a small TPC. I believe it's a 3 centimeter drift length, and it has been mainly developed to characterize a charge tile, and a couple of papers have been published here. I reference one of the, I believe the most recent one. And the light, as of now, is mainly used as triggering, and of course for the drift time calculation. So far, the light readout system, the main feature is that there are 24 1x1 SIPM, and these are gained into 12 different channels. So it's 2 devices per channel. And it already has a cold front-end electronics. What we are planning to upgrade is to scale and have a 10-fold increase in the light sensitive area, and actually optimize let's say the coverage, the geometrical coverage of the SIPM. So limit as much as we can, let's say the dead space, the non-sensitive space on the tile. So in order to do this, we built a ceramic tile, and we basically populated this as much as we could with SIPM, and we were able to pack into let's say into 2 semicircular tiles of 180 millimeter diameter, a total of 200 around 200 devices divided in 32 different channels with 6 SIPM per channel. And the signal is still read out by 2 electronic board at cold temperature, not in liquid xenon, just cold. And after this, they are set out at room temperature for the digitization to the ADC. You can see a couple of pictures from the assembly. On the let's say on the top left, you can see one prototype of the tile with just 2 channels. I'm not sure. Can you see my pointer? I guess.
I don't think so.
Oh,
yes,
okay.
yes.
Okay.
Yeah.
So yeah, so you can you can see the 2 ceramic tile assembled with just 2 channel, 1 per board, and on the bottom you can see how the signal are read out by 2 flex board that are going to the feed through here, and underneath there is the let's say the readout can with the boards, the front end boards. Here is a bottom view of this flex board. These are made out of Kapton, which we believe is one of the let's say more cleanest solution for this kind of circuit. On this picture here, you can see the let's say photosensitive and cathode stack. On the top, you can see the cathode mesh, and underneath there is the tile. Here you can see a detail of the wire bond that is going to carry the bias to the devices, to the SIPM, while the back is going to be the signal readout. Here is the entire stack with the cell closed. On top here there is the anode with the charge tile, and then on the bottom flanges this stack here, and everything is ready.
Sorry, you should speed up a little bit. There is maybe 3-4 minutes left.
Oh, okay, that's right, because yeah, you're right. Okay, so let me describe very quickly the SIPM. These are made by these are VOV sensitive and are manufactured by a custom run at FBK, 1 centimeter square each. And in let's say in preliminary analysis, we noticed that some of them have early breakdown or kinks in the IV curves. And that, of course, it's a problem because, let's say, if we apply the same voltage across the different channel, we're going to have very non-uniform gain in the light readout. So what we decided to do was to have an independent, each channel by channel, an independent voltage source. And this is how basically we decided to implement. So on the board, there is going to be a programmable voltage source that actually doesn't need to have 32 different channels going into the detector. But since we are using, let's say, a DAC that for that DAC that are daisy chain, we actually can program 32 different biases with only 4 lines. 1 is analog and 3 digital lines. And then on the readout side, and then everything, of course, it's fed into the different SIPMs. And then on the readout side, there is basically a transimpedance amplifier, and this is, you can see the gain here, and everything is going to the ADC. And this is 32-fold. You can see where the location of these different components are. This is in liquid. This part and this part is on the board, while this is in the liquid and it's on the ceramic tile. Here is how it looks in, let's say, on the board itself. All the different components have been tested at liquid xenon temperature. So we know that the single components, all the single element in the circuit are working and compatible with this temperature. This is a preliminary test that we assembled. So basically, we closed up the cell at room temperature, not cold yet, and we just pulsed an LED. And you can see from this plot right here that although we suffer some high frequency oscillation, we are sensitive to the light, and actually, so that the devices are active. At the same time, we are also working on simulating the light response and the light collection across the chamber. And to do this, we're using Chroma, which is a GPU-based package for photon transport simulation, and it's going to be the same package that Nexus will use. So it's also a useful test bed for this software. So this leads me to the conclusion, and as you can see, we still need to do some work in terms of fixing this, let's say, this oscillation that you saw, but we believe that the sensors are active and we are able to read them out. ultimately, of course, we want to do some preliminary testing code and be able to observe the dark rate of this channel of these devices, and hopefully measure also the single photon. And at the same time, on the simulation side, we will work on the light map production so that we can let's say cross-check what we measure with what we expect from the simulation. I'll leave here the conclusion. So if anybody has a question, I can answer the question and you can read the conclusion.
Thank you very much. We have time for one quick question. Okay, so thanks again, and let's move to the next talk. So Teal Pershing will tell us about direct detection of argon scintillation light using UV-sensitive SIPMs.
Okay,
so
can you hear me okay?
Good? Yeah, perfect.
Okay, great. So yeah, thanks for the introduction. So my name is Teal Pershing. I'm a postdoc at Lawrence Livermore National Laboratory, working with Jinka Xu. So I'll just get right into it. A little bit of background into direct detection of argon scintillation light with these SIPMs. So as we've seen a lot today, the majority of scintillation light that you get from argon when you have particle interactions in it, either in the gas or in the liquid phase, primarily emits in the hard UV, so somewhere around 120 to 140 nanometers, as you can see from a past measurement that was made here on the right. And so direct detection of this, short of a wavelength, is pretty tough. A lot of commercial photosensors don't really have the quantum efficiency at these short wavelengths. They're kind of at longer wavelengths, so you use wavelength shifters generally to shift this UV light to more sensitive regimes for these photosensors. Now, as we've seen today, when you do that, there's other considerations and things you have to take into account. So just thinking about your long-term stability, if how you've actually deposited the wavelength shifter, if you have any non-homogeneity concerns, and then also you can lose some time and position information from the absorption and re-emission. So if those are things that are of concern for you, it's ideally it would be great if you can instead just directly detect your scintillation light and not have to worry about wavelength shifters. So Hamamatsu has developed a generation of UV sensitive SIPMs that have appreciable photon detection efficiency down at argon scintillation emission wavelengths. So the quoted PDEs from Hamamatsu for the previous generation of SIPMs, and then sort of the current one, the VUV4, which we're using, are shown on the bottom right. And so in our group, we're particularly interested in using either the S13371 or S13370 packages that you can just get commercially from Hamamatsu. And so the main goal for a measurement that we're working on right now is to quantify the performance of these SIPMs for directly detecting argon scintillation light, and then also general operation in liquid argon in future detector deployments. Okay, so just a short note that we are using onboard cryogenic amplification. So kind of the main motivator for this is that for the same gains you can run at lower over voltages, so you don't have to worry as much about your dark noise and your crosstalk potentially. And then there's trade-offs and difficulty of using cryogenic amplifiers. But we're using the Texas Instruments LMH6629 amplifier right now on our board. In the upcoming publication that we'll do some of our work, we'll give more details on the board we're working, but it's heavily influenced by the circuit schematic that's in the Dineco publication from 2017, and then also some initial communications with Alessandro Rosetto at Princeton and Gran Sasso. And so we're going, we then sort of took the circuit schematic though and kind of ran with it, making our own PCB board design that works for the Hamamatsu SIPMs. And so we're using a 2-board design right now with the idea of we have one mounting board, which amplifier boards with SIPMs plugged into them will be able to plug into, so that as we scale up for detector deployments, we can have this modular design where we can put SIPMs, which SIPMs we want, where we want, on sort of a single mounting board. Oops, there we go. Okay, so for our first tests of some of these boards, we've developed a SIPM test cell that we can mount these amplifier SIPM boards to. So a diagram of the SIPM test cell that we're putting in our argon condensation test stand is shown on the top right. So we have 3 SIPM amplifier boards that we're using. One has 4 of the S13370 packages, windowless, and they're they're mounted in parallel, all routed into a single amplifier. And then we have two S13371 packages, one that has a quartz window and one that does not have a quartz window. So the idea here is that the quartz window is going to absorb, around below 150 nanometers, depending on what kind of quartz you're using, but it should absorb that VUV scintillation light. And so the difference that we see in the two SIPM units will give us an extra handle on quantifying, how much hard UV light we're seeing in the windowless SIPM unit. And so the entire cell is going to be submerged, is submerged in liquid argon in a detector can. And so this kind of what this looks like in person is on the bottom right and the bottom left here. So you have the three boards just mounted into this metal cell, and this is attached to a flange which we put into our liquid argon condensation test stand. And so we're able to maintain, we can condense liquid argon and maintain it at a constant temperature and pressure. And this entire test stand is eventually going to be evolving into a xenon doped argon test stand that we're going to be using at Lawrence Livermore National Lab. And so Keith and Bernard's talk tomorrow for more information on this. I don't want to get too much into it, but as it is right now, it's just a can that we can use to condense liquid argon. And so we did this and fully submerged the SIPM cell and liquid argon. And then after doing this, turned on our SIPM amplifiers, and then outside of the detector space, we put an americium-241 source. And so we took all of our first data with americium-241. That'll be all the data that I'll be showing for today. We did some preliminary pulse identification using the DACMan software package. And so there's a GitHub repository here for the open source software for that. And it allows flexible tuning of what kind of pulse sizes and shapes you're going to actually be identifying as pulses. So you can do single pulses for gain calibration for the SIPM amplifiers, which we did for all of our boards. And then after that, you can also do either full waveform identification or just selecting specific regions for characterizing the argon scintillation light time profile. So an example candidate americium-241 event in one of our SIPMs is shown on the bottom right here. Okay, so using the pulse and waveform reconstruction, the first thing we looked at is we averaged over entire waveforms for both of the windowless SIPM boards, so windowless S71 and then the 4x70 unit board. And we required at least 5 PE in an event to make sure that we're not picking really any of the dark pulses for the most part. And so the average waveform shape is shown here on the right. And so first we just did an exponential fit in sort of the delayed window to see if we're getting the expected slow scintillation component that you want for argon. And so we measured for a first fit 1.54 microseconds, which is good to see. It seems to be in agreement with some of the literature. Just some numbers from Hitachi from '83 are shown on the bottom right. And then for a first estimate at the prompt to total charge fraction, the window is shown in the image on the right. And so using that window, the first prompt to total charge fraction is 0.32. So obviously there's going to be, we need to incorporate in systematic uncertainties for the window that's picked and the pulse shape and whatnot. But for a first pass, it's looking like it's in the right neighborhood. So we're happy to see that. And then from there, we did a comparison of the windowless to windowed S13371 units to see if we saw a difference, which would indicate that we're seeing the very UV, the VUV scintillation component. And so on the right, the blue curve is the total pulse integral from -1 to 11 seconds centered around the trigger to sort of try and collect the entirety of the of americium-241 gammas. And you can see the window unit sees very little light. For the most part, you're just seeing 0 to 1 PE pulses, maybe a little bit more. And then in your windowless unit, we see a clear sort of second distribution in a higher PE space, which we expect is due to the americium-241 gamma. So we're pretty convinced that we're seeing VUV scintillation light from gamma scattering inside of the liquid argon in the test cell. So from here, it's the data seem to indicate that we're getting our first, for our group, our first detection of this argon scintillation light. And so the plan from here is to sort of do a further detailed analysis where we'd like to try and calculate out the photon detection efficiency and compare that to the quoted values for Hamamatsu, and then sort of go further and trying to just calculate the general characteristics of our SIPM amplifiers, gain versus voltage, dark noise, crosstalk, and so on. So I think I'll stop there and I'll take questions.
Thank you. Any questions from the audience?
I cannot raise my hand, but can I ask?
Yes, of course. Go ahead.
So from the simple, say, geometrical light collection consideration, can you estimate what's the detection efficiency of this light, argon light, by this windowless PM, silicon PM?
So that's the plan, is that we're planning on trying to do a full optical simulation of the can, and then try and compare those results to what were actually the PE numbers that we're detecting for a given source put, you know, just outside of the cell. So that's our sort of current approach for trying to calculate the PBE.
Okay.
I see a question from Ryan Durrell.
Yeah, just wondering if you have plans to use any other radiation sources or light sources, maybe even like a UV LED could be another way.
Right. Yeah. So that we don't have plans for that right now. We're planning on just using sort of different energy sources and really focus on trying to get what we can from directly the argon scintillation light in our test stand. But that is something that we can consider in the future. It's just it's not the test stand isn't really set up for that right now. But it is a consideration if we can find a good UV source that is sort of emitting in the you know, in the argon scintillation range too.
I'm wondering what does actually windowless mean for that particular SIPM? Does it have any anti-reflective coating? Is it bare silicon with a layer of oxide, or something else? Do you know?
Yeah. So and when we're referring to it as windowless, the Hamamatsu packages by default, they come with a quartz window in front of sort of the silicon, so the main like chip. And so we just took that front window off. Other than that, we haven't really done anything to the front of the SIPM to change it from, you know, what Hamamatsu provides commercially.
Okay, so I see. This wasn't optimized in any way by Hamamatsu to these very low wavelengths.
No, I don't think so. I mean, I think they're trying to head that direction to provide something that, you know, can be more sensitive in this range. But aside from, you know, just taking off the quartz because it does absorb in that sort of, you know, hard UV, we haven't done anything.
I see. Any more questions? Okay, thank you very much. We have one last talk in the session from Polina Abratenko, overview and current status of the X-Arapuca light collection system in SBND. Polina, could you please share your slides?
Yes, 1 second. Okay, do you see my slides?
Yes, this looks fine. You may want to.
Is this better?
Yeah, perfect. Yes. Please
Okay.
go ahead.
All right, so my name is Polina, and oh my gosh. My name is Polina, and today I'll be talking about the, I'll be giving an overview of the current status of the X-Arapuca light collection system in the SBND experiment. So first, table of contents. First, I'll briefly talk about the SBND experiment, including the photon detection system. Then I'll go over the X-Arapuca light collection system specifically. And then finally, I'll talk about status of testing and implementation of the system. So the SBND is the short baseline near detector. It's part of the short baseline neutrino program at Fermilab, which is a series of 3 detectors. The program aims to search for light sterile neutrinos, perform neutrino interaction measurements, and probe beyond standard model physics using liquid argon time projection chamber technology. So SBND is out of the 3 detectors, it's nearest to the booster neutrino beam target, and it is currently in the construction phase. The SBND photon detection system plans to employ two sets of photodetection technology. So one of these is a set of photomultiplier tubes, and another is a series of X-era Puka devices, which I will focus on in this talk. If you want to know more about the general SBND PDS, there's a talk about that tomorrow. So yeah, in the SBND PDS box, we have these X-era Puka units. Two are shown here in this model. And each of these units contains an array of silicon photomultiplier boards or SIPMs. Some more about an individual unit. So one X-era Puka unit is basically a light trap. So here is a diagram on the right of the components of a unit. Basically, light enters through the top window and hits a dichroic filter, which transmits photons below a certain cutoff wavelength. This wavelength is then shifted by light guides. It shifts the light inside to a wavelength where the filter is reflective and traps the light. And this trapped light is collected by a set of four boards containing an array of 8 SIPMs each. So here's an example of one of these boards, and for simulations of these optics, you can see a poster by Gustavo. Yeah, so in SBND, a total of 192 of these X-era Puka devices are planned to be installed. Important to note is that 176 of these will contain Sense SL SIPM boards that are tested at Fermilab with something called the Daphne readout. And they look like this board here on the top, while the other 16 X-era Puka units they contain a different type of SIPM, Hamamatsu SIPMs, and they'll be tested at in Unicamp in Brazil with a different readout called Epsia. So that's what this board looks like here. I will be talking about these 176 that were tested at Fermilab in this talk. So something else important to note about these units is that half of these will be sensitive just to visible light, while the other half will be sensitive to the UV light, which is sort of something special to SBND. Overall, though, we will be using the same components as planned for Dune, just with different design. So the status of these units is all 192 modules have been fabricated, assembled, and delivered to Fermilab. And we are currently awaiting the cabling of the SIPM boards themselves to these units. So here's just a picture of the modules arriving from Brazil. So yeah, I'll be talking about the one type of board associated with the Fermilab test that I mentioned earlier called the XTDB or X-tongue depressor board. So this board is a set of 4 3x3 millimeter squared Sensel SIPMs that are wired in parallel. And then we have 2 6x6 active arrays wired in series to make one channel. The anode and cathode signals are connected via the backplane of the board for the bias and signal distribution. And we also have 2 500 kilo ohm resistors to split the bias on the board as well. So in terms of testing, we perform qualitative tests on these boards that will be used for the actual install in SBND. So that's 704 of these XTDBs plus a set of spares. And the qualitative tests we were performing included testing if all of these boards are able to see light in both warm and cold, and also determining the failure rate after cold cycle, if any. So a basic schematic of our setup was that we have a dark box where we place our SIPM boards, in which we have an LED that generates a flash, given the pulse generator. And then the readout of the boards is read out through these Daphne electronics, and we see waveforms on our computer. So a little bit more detail about that is we use the 40-inch tall cryostat as our dark box. This had a foam and wood lid for insulation with holes cut through it to have, feed through for the electronics, as well as the liquid nitrogen and gas nitrogen fill lines. So on the structure connected to the lid, we have a custom PCB where we attach our boards. On one side of that, we have 10 LEDs. And on the side of this vessel, we basically have resistance temperature detectors to measure the level of liquid nitrogen when we fill. So here's a picture of the actual setup. You can see the lid connected to the structure with PCB with our boards slotted in and all of the cabling. And then on the right here, you can see the LED array on one side of the board using UV 395 nanometer LEDs to flash the boards. And this is just a picture of the vessel closed. So we could see the liquid nitrogen fill line as well as the switch box for controlling LEDs. So testing setup. Basically, each Cat5 or Cat6 cable is split up into 4 channels, and each one of these channels connects to 1 slot on this PCB, which we created with 100 slots total using 50-pin connectors going to RJ45. And a slot may or may not be occupied by an XTDB. So that just means when we take data, 1 or more cables may be empty. And this is actually significant because we were not able to perform tests with all of these slots filled since we observed shadowing. So basically, since our LEDs were on one side of the board, the PCB, the boards in front blocked the boards in the back. So we had a lower occupancy in the back and a staggered position of the boards. So in terms of optimization over time, we determined 59 XTDBs slotted in was an optimal number for our tests. So a bit more about our readout. We use the Daphne electronic system, which is one of the systems specifically developed for X-Arapuca radar and SBND, but it is also the basis for the FEBs that will be used in Dune for the horizontal liquid far detector PDS. Our readout in these tests was a trigger in coincidence with an LED pulse provided by our pulse generator in burst mode, and we acquired 200 waveforms per channel per test. So here we just show the slots being connected via Cat5 or Cat6 to a converter board, which connects to HDMI to the Daphne front end board, and then that connects to our computer and power. So our data taking procedure from front to end is first placing the boards on this PCB. So as I mentioned, there are some higher occupancy zones closer to the LEDs that were less prone to shadowing, and lower occupancy zones in the back. And just to note that early on in the procedure, slotting the boards in and out, some resistors would come off. So we fixed that very early on. And overall, we were able to have a constant occupancy of more or less 59 boards towards the end of the procedure. After the boards are slotted in, before biasing any of the boards, a very crucial step was to check the resistance on each channel, which would read a nominal value of 1 mega ohm or open line on empty channels, and would not read the correct values if there was something wrong. So for example, if the boards were not seated correctly, if there was a problem with the cable, if there was water from condensation from a previous fill, that would also not read the nominal value. So this is a very important step before performing any tests. So the next part of the data taking procedure after this was performing a warm test. So with a closed vessel without any liquid nitrogen using the Daphne electronics. I'll show data in the next couple slides. Then we would fill the vessel with liquid nitrogen. You see the dewar connected to our fill line. And then we would perform a cold test, which was almost identical to the warm test. And again, we would check resistance values before biasing the SIPMs. Then we would empty the vessel, which is actually the longest part of the procedure. It would take over a week to naturally boil off. So we speeded the procedure by flushing with nitrogen gas. And then once we were at room temperature, we flushed for an extra day to remove water condensation. Then we performed another warm test after the cold fill and checked the resistance values again. And this one cycle will take around. Saw in our data, these are examples of waveforms. So our signal is a pulse above the noise levels on a slot with an XTD slotted in. So these 4 plots is an example of 4 channels on 1 cable. The 2 on the left have a board slotted in and the 2 on the right do not. So we see on the right, there is some environmental noise that does not affect our test results. So we see the crosstalk on these empty channels. And then our signal, which is a pulse above the noise levels, can be seen on the channels with boards slotted in. We see clear pulse here. Another example of what we saw is correlated interference. So for example, these are 2 channels on the same cable. And on the left, we have a saturated light pulse. But on another channel with a board slotted in, we would see this correlated interference feature. So this made it unclear if this board actually saw light or if we just saw crosstalk. So basically what we did is these channels were retested after reconfiguration of either the LEDs or position on the PCB. So reconfiguring LEDs, this meant, turning some LEDs on or off, seeing if we would continue to see this feature on this particular channel, and changing the position on the PCB itself, since this was after the board was actually all closed up in the vessel, which may or may not have been a warm or cold test. Basically, we would change the position on the board and do another test with this same XTDB. So yeah, overall our results, a total of 777 XTDBs were tested at both warm and cold temperatures, and were able to see light. This includes the 704 required XTDBs that will be installed in SBND, as well as a set of 73 spares. Overall, we only saw one quote unquote bad board. This was very early on in the testing during the development stage. So we determined the overall failure rate was actually less than 1 out of 777. And we're currently working towards the next steps on SBND, which means cabling these boards together after these tests, general assembly of the X-Arapuca system, and then finally placement into the TPC.
Thank you very much. Are there any questions from the audience? Don't see any raised hands. Could you elaborate why SBND needs both visible and VUV sensitivity?
Yeah, so that I think that's basically an R&D choice to have some photo detection that's only visible to visible light, like Cherenkov radiation, as opposed to I guess like to separate from the photo detection that is sensitive to the VUV. So that's something that's not really, to my knowledge, has not really been explored a lot. So I think this would be interesting for, yeah, just analysis for new physics.
Okay.
Yeah.
Thank you. Any other questions? Matthew and Ana Machado.
Yeah, just to chime in, I think following up on what Ana said in the chat, you'll hear tomorrow from Vincent Bask a general overview of the SBND photon detection system. And there's an important passive element that's in SBND, which is a TPB coated reflector foil that goes on the cathode. And so that will produce a lot of visible light that can be separated from the VUV light that directly illuminates the photon detectors. And there's a lot of interesting things you can do there in terms of X dependence, meaning drift dimension dependence of the interaction and imaging. But I think for more details on that, that'll be covered by Vincent tomorrow.
I guess I can imagine the usage of visible light easily, but I'm more wondering what VUV is needed for in SBND.
So the scintillation light from liquid argon is naturally VUV. It's 128 nanometers. And when we say VUV, we actually mean there is a wavelength shifter on the surface of the X-Arapuca device or the PMT that will convert it into visible light so that it'll be seen by those photon detectors. When we say visible, we mean it is not directly sensitive to that light. There is no commensurate ability to see that, and it has to see the light that's being reflected from the cathode, so indirect. So you might think of it more as indirect and direct light in SBND, okay, based on this passive element.
Now I understand, thank you. Okay. Was there any other question or comment?